As has become our pattern apparently, we will start this lecture with a new notation. So I'm going to organize it the way I always have been: syntax, semantics, and then formalism. So syntax is just grammar, and here's the way it works. So the notation requires two ingredients, a term and another term. Stick a comma between them, and then instead of putting curly braces like we would for a doubleton construction, we put parentheses. And overall, what you will get when you do this is a term. So that's it for the grammar. It is a way of combining two terms to get another term. And in terms of meaning, well, let me just give you the name of this construction. People will call this an ordered pair. So like this, two objects with parentheses and a comma. And you'll see why the word ordered is getting used there in a moment. Sometimes it's just called a pair. So it's really meant to be nothing but a package that consists of these two things. But it's a little bit different from a doubleton because the way it's intended to work is that, well, it's ordered. So there's a first position and a second position. With a doubleton, there's no such thing. So remember how with doubletons, the doubleton of two things is equal to the doubleton with the things written in the other order. So this is partly why I've been drawing sets as bags of elements. They don't care about the order in which things are written. They just, for any given thing, it's either in there or it's not, and that's it. That's the only information that's contained in a set. An ordered pair is going to be different from a doubleton because it does care about the order in which things show up. Okay, so is this a brand new construction? It sounds like it's not a set, right? It sounds like something totally new, a different kind of object. So far, all we've seen are sets, and here's our first non-set, right? Wrong. Well, it could be right. It depends on your approach. You could set things up, when you're developing this language, you could set things up so that there are two kinds of things. Some things are sets, and some things, rather than being sets, are pairs, or sometimes they're called tuples. And those are just different kinds of entities, different species. And you treat them differently, and they have their own different axioms. So axiom 5 helps you work with sets, and then we'd create a new axiom that helps us work with ordered pairs. That's a way we could go, but that is not the way we're going. So what we're actually going to do instead is try to fold in the concept of an ordered pair into our set theory. And people will do this whenever they can, actually. Try to, instead of creating new axioms to build up a brand new theory, instead make those actually be definitions within set theory, so that we just have one unified theory, set theory, that contains within it models of all these other axiomatic systems that you might have in mind. So an ordered pair will be a set, but it's not the set that it looks like it is. It's not the doubleton with curly braces x, y. So it's not the same as this, but it will be a set. So what set? So here it comes. So the ordered pair xy, this is a definition, the ordered pair xy shall be a doubleton consisting of two items, one of which is a singleton, and the other of which is a doubleton. And it'll work like this. Take the first thing here and put it in the singleton, and then take both things and put them in a doubleton like this. Okay, so why in the world are we constructing or defining ordered pairs like this? The answer is because it makes them behave in the way we want. It makes the theorems about them that we would like to be true end up being true. So, I've always told you that syntax is the grammar, the semantics is the intended meaning but does not help you prove anything. The formalism is what helps you prove things. So that's true that this is what helps you prove things, but it's actually not the best go-to if you want to prove anything about ordered pairs. The best go-to is the theorem that comes immediately after this definition. So this is theorem 39, and it tells you exactly when, so if and only if, it tells you exactly when two pairs are equal. Two pairs are equal if and only if their first positions match up and their second positions match up. Notice it's not like that at all for doubletons, right? Compare this to theorem 23 here, where you see that if two doubletons are equal, if the doubleton xy equals the doubleton uv, then you cannot conclude that x and u match up and y and v match up. They might, but it's also possible to have x match up with v and y match up with u. So this is another way of observing that doubletons don't care about the order in which things are listed. By the way, since I keep using the word doubleton, maybe I should remind you once again that I'm pretty sure I made that term up, and it's not a real word. I think people would just call this a set with two elements. Maybe, although you don't know that it has two elements, right? Because it could be that x equals y. So, I don't know, a set with at most two elements. But I'm just going to call it doubleton because singleton is a real word and it just makes sense. All right, back to pairs, which are different from doubletons. So the title of this theorem, theorem 39, it shows up down here, right after the definition of ordered pair, theorem 39. The title is essence of pairs. Remember I told you before about essence of theorems? I'm choosing to put this title, essence of, for any theorem where the theorem is actually more important than the definition. So the fact that it says essence of here is suggesting to you that probably actually you shouldn't care that much about the definition. And this is the fundamental fact to use if you want to prove things about ordered pairs or use ordered pairs in some way in your proof. So the definition is here just so that we don't have to create new axioms, so that we can fold in the theory of ordered pairs, if you want to call it something fancy. So we can fold that into our set theory, rather than creating it as an independent theory that we sort of tack on with new axioms. So what I'm trying to say is forget about this definition and just be comfortable in the fact that it exists and it makes this theorem true. Okay, that being said, I'm going to prove this theorem in the next video, but that will be a bonus video. So you can actually skip the next video and then go to the one after that instead. So the next video is optional. All right, and before I end this video, just because I've been showing you the LaTeX for all notations, the LaTeX for this one is pretty simple. You just, you literally type parentheses and they show up as parentheses.